So let's just look at a little bit of the context of hashing in practical applications. As I mentioned, it's very widely used. So here's an example right from Java. The first implementation of Java 1.1, the designers found that the cost of computing the hash function for strings seemed to be excessive, particularly for long strings. And that was one of the main uses of hashing, was just to be able to do searching with string keys. And so what they decided in the first implementation was, let's just look at every 8th or 9th character. In that way, we don't have to spend a lot of time computing the hash function. So they had a hash function pretty much like the one that we use, except they'd compute a skip that would mean that they'd only look at about every 8th key, and they wouldn't have to do quite so much work performing the hash function. And that's definitely one thing to consider when using hashing, is that the cost of computing the hash function for a complicated key might exceed the cost of searching using a simpler structure like a binary search tree. And anyway, for Java 1.1, what happened was that there was a huge potential for really bad collision patterns on typical data. So here's an example of typical data, which is a URL. All of these keys, which are totally different, would wind up having the same collision. And so client programs and system programs in the Java system were having terrible performance on their symbol table because of this shortcut in hashing. So this well illustrates that you need to use all of the data in the hash function. And sometimes when you do a closer analysis, the cost of the computing the hash function can mean that something like red-black trees will even outperform hashing even for just search and insert. So there's another thing about the uniform hashing assumption, is that it is an assumption, and if you're writing code where we have to have guaranteed performance, like when your aircraft is landing or you're controlling a nuclear reactor or somebody's pacemaker, if that assumption doesn't hold and you get bad performance, you're going to have disastrous consequences. So that's another reason to think about maybe paying a little extra and using the guarantee that you get with red-black search trees instead of hashing. And there's another surprising situation that happens in today's world. For example, Java publishes its hash functions. And so if you're trying to provide a service over the web, an adversary can learn your hash function and just send you data that causes a huge performance problem by just making all that data hashed to one particular item. And that's definitely something to worry about. And in the real world, you can nowadays find on the web particular sequences of keys that will cause particular services to crash. And again, that's a little harder to do with something like a red-black tree where we have performance guarantees. When you make an assumption, you better be sure, and you're depending on that assumption, you better be sure that it holds somehow. And this is different than, for example, for quicksort, when our assumption was we're going to create randomness and we're going to depend on that randomness. In this case, we're kind of hoping for randomness, and maybe that doesn't really always hold. So that's certainly something to be aware of when using hashing in practice. So here's just a simple example on hashing in Java. What we can do is it's pretty easy to find a family of strings that have the same hash code. For example, with just a little fooling around, or nowadays you can just look it up on the web, you can see that these 2-character keys both have the same hash code. And you just do the math, and that base 31 hash code will tell you that answer. Well, what that means is that actually, just like working in binary, you can combine those things in all possible ways, and you can get 2 to the n strings for any n of length 2n that all hash to the same value. And somebody's implemented a service in Java that uses a symbol table that takes string keys, you can cause that to crash in this way. A little bit scary for some systems designers, at least reason for pause in using hashing. Now, hashing also has an extremely important application in today's internet commerce. It's the concept of so-called one-way hash functions, which means that we use it for secure, to try to have some secure fingerprints for use on the web. And there's been a lot of research done to develop functions that take keys as input and then produce values that look random in such a way that it's hard for someone else to find another key that collides with that. This technology is useful for storing passwords and digital fingerprints and things, but it's too expensive for use in a symbol table. So the bottom line is separate chaining versus linear probing as collision resolution methods. There's a number of considerations to take into account. Separate chaining is really easy to implement, both insert and delete. If performance degrades, it does so gracefully. And the clustering is maybe less of a problem if you have a bad hash function. Linear probing tends to make better use of space, and also it'll perform better for huge tables where caching is involved. And classic algorithm or computer science problems for people to think about is what do we do to delete in these two situations, and exactly how do we resize? And those are all at the level of exercises in the context of the kinds of algorithms that we've seen. And as I mentioned, there's been many improved versions of hashing that have been studied. I mentioned the two-probe or double hashing version. Another way to use two hash functions is just to hash to two positions and put the key in the shorter of the two chains. In that case, then the expected length of the longest chain will be log n, which is quite an improvement. You get constant time expected and log n worst case. Double hashing is the variant of linear probing where you just skip a variable amount, not one each time, and that pretty much wipes out clustering, but it is more difficult to implement delete for that one. In a new method a relatively new method called cuckoo hashing, is another variant of linear probing where we hash a key to two positions and insert the key in either one. If occupied, you reinsert the displaced key into its alternative. It was in one, each one can go to two. And that one actually gives constant worst case time for search. That's another variation on the theme. And all of these things allow us to make better use of the memory, allow the table to become nearly full. Would have been very exciting to the researchers in the 1950s who cared so much about memory. Nowadays, a little extra memory is not something that people care about so much, and most people just go with the easy algorithm, except for really performance-critical applications. What about hash tables versus balanced search trees? Well, hash tables are really simple to code, usually, if you don't have to do the hash function. And if you don't have order in the keys at all, then you need the compare to implement balanced search tree. So you have to use hashing if you don't have comparison. And it'll probably be faster for simple keys to use hashing. It's a few arithmetic operations to do the hash versus log n compares for the balanced tree. And there's some better system support in Java for strings. That cache hash code means that you don't even have to compute the hash if your symbol table for strings is in an inner loop. On the other hand, balanced search trees have a much stronger performance guarantee. You don't have to assume anything. It's going to be less than log n compares, and it's got support for all those ordered ST operations, and compare to is a pretty easy and natural function to implement. So it's more flexible and more broadly useful. And actually the Java system and other systems include both, so that programmers can make use of either one in different situations. that's our context for hashing algorithms.